Hello everyone, now we are going to study about the performance of the Francis turbine. Here also we have to going to study the performance by two methods. One is the constant speed as well as the constant head, how we are studied in the Pelton wheel. The main parts of the Francis turbine we are going to first discuss. The main part is what one is the penstock, that is the pipe connected to the turbine from the dam actually. Next, it is consisting of the runner. Here you can see that one. This part is the runner, and outside this blades, what the blades we are seeing, that is the um, guide vanes. And at the same time, we can see this spiral casing also. Spiral casing. And the next important part of the Francis turbine is the draft tube. The main parts of the Francis turbine is the penstock, runner, guide vanes, and the spiral casing as well as the draft tube. For this experiment, the important parameters for the calculation purpose are: one is the turbine speed, ammeter, voltmeter, as well as this energy meter disc rotation, and well as the head on the turbine. Mainly we required the head on the turbine and also the turbine speed in RPM, as well as the what is the energy consumption by the energy meter. That one you are going to calculate from the energy meter disc. And at the same time, the next is what is the pressure acting in the draft tube, and the flow rate using the V notch. Initially we have to set this scale to the zero level in the zero, means we have to set this needle at the water level in this column. In this experiment, the load is done by this AC generator. The load is acting on the turbine, that is by the AC generator, by on the 200 watt bulbs. Here in Pelton wheel we use in our experiment Pelton wheel, the load acting on the turbine is by the brake drum, but here is the AC generator. Now we are going to conduct the experiment for the constant head. Exactly same for the constant speed also. First, on the turbine, set this valve, load down the head on the turbine. Now we are going to apply the load on the turbine by switching on the bulbs. When you switch on the bulb, you can see that the speed is reduced, and the head on the turbine is almost the same thing. If head on the turbine is reduced, using this valve we have to maintain the constant head on the turbine. Now the reading should be noted down. One is the voltmeter, ammeter reading. Next is what is the speed, and for a 5 revolution of this energy meter disc, how much time is taken, that should be noted down. Next is the pressure acting in the draft tube, that should be noted down. Next, find out the flow rate from the turbine. Just place that needle, just touching the surface of the water. Later, note down the scale, how much it is increased. Initially it is in the 0 level. Now it is increased to 20 centimeter. This is the head over the notch, V notch. This is very useful for during the calculation purpose. The experiment is repeated for the different load by on the electric switches, electric bulbs. The same type of experiment is conducted for the constant speed also, where in that one we are going to maintain the speed is the constant. Thank you. Now the next is what we are going to discuss about the calculation part of the Francis turbine. Okay, the Francis turbine experiment part is over. Now we are going to discuss about the calculation part. Francis turbine calculation part. Here also the experiment you are going to conduct in the two methods, constant speed and constant head. Similarly, what you did in the Pelton turbine, Pelton wheel. For the calculation part, first we have to fix the guide vane position, but this will not comes in the calculation part, but different discharge we can do the experiment. Here, once again, the constant speed. In constant speed, what will happen? The speed will be constant for all the readings, and head over the turbine that should be taken. That is what in terms of kg per centimeter square is there. And in the same time, you have to take the vacuum pressure that is adopted in the draft tube. You have to take these two pressures, and that should be calculated on the net load on the turbine. Net load on the turbine H can be calculated by using this equation. That is what 10 into X plus PV divided by 760. PV means this is what that is the pressure, vacuum pressure taken on the draft tube. And this is the head on the turbine. If you have to multiply by 10 to convert meter of water. So head over the notch that is be taken from the V notch. That is useful for to calculate the actual discharge, and load on generator. Volts as well as amps should be noted down from during the experiment. Next, energy meter readings. For a K means for a 3 rotation of the energy meter disk, how much of the time is taken, that should be noted down from the stopwatch. Next, what is the bulb we are on, whether it is a 200 watt or a 400 watt or a 600 watt bulbs we are on, that should be noted down here already. These are the values you are taken in the during the experiment. In the experiment, you are going to take this value, head over the notch, this one, and these are the values that will be taken in the during the experiment itself only. And this also wattage of bulb on action, that is also be taken in the during the experiment. Q actual can be calculated using the what head over the notch, and the equation is very simple, so many times used. This is the equation should be used to find out the actual discharge, and head of the turbine is over. Then input power can be calculated by using this one, rho q g h. We know the discharge, h is the turbine, head of the turbine, you know that one. Rho is the density of water is 1000, g is the acceleration due to gravity, that is 9.81, divided by 1000 to convert it to kilowatt. Output power can be calculated by number of disk rotation into 3600 divided by energy meter constant. This is the energy meter constant present in the experiment itself only. In the energy meter disk only, this energy meter constant is printed. The value should be noted down from that one. This is the observation value that is also available in the experimental setup. T is the time taken for a rotation of K rotation. Here you take another, you can take K is equals to 3 rotation or K is equals to 5 rotation of the energy meter disk, how much of the time is taken. That should be noted down from the stopwatch. And this is the equation, and multiplied by the mechanical efficiency of the motor. Mechanical efficiency of the motor you can take another 70%. And output power you can be obtained using this equation. Finally, the efficiency can be calculated by output by input, we will get the efficiency. This is the part for the constant speed calculation. And next is the constant head. Constant head is also the calculation part is everything is same, but in the constant head you are going to have the unit power, unit speed, unit head, and specific speed of the turbine. These are the things we are going to add it, and the equation is same thing what you used in the Pelton wheel. Up to here, what are the equation used for the constant head? Same thing. For the constant speed, what are the equations used are the same thing. Next, for the constant head, for to calculate the unit power, we are going to use these equations. These equations we are going to use this one. And this is the calculation part for the Francis turbine. Thank you. And this is the characteristics curve should be obtained after the calculation during the plotting the graph. Okay, all those things we explained during the experimental. Francis turbine, the guide vents, the runner, as well as the spiral casing, everything is we